Somewhere right now there is a river. Maybe you can hear one if you listen carefully enough. The slow pull of water over stone, the patient carving of valleys that took 10,000 years to form. Rivers have always been here, longer than cities, longer than language, longer than memory. And yet, woven into nearly every culture that ever built itself beside one, there is a story. A great flood came. The waters rose. Almost everything was lost. That story shows up in Mesopotamia, in ancient India, in the oral traditions of indigenous peoples across the Americas, in the myths of Greece and China and sub-Saharan Africa. It appears in the Epic of Gilgamesh, one of the oldest written texts we have, carved into clay tablets thousands of years before the Bible was assembled. It echoes through the Hebrew scriptures, through the Quran, through Hindu cosmology. When a story repeats itself that persistently across that many unconnected cultures, you have two choices. You can call it coincidence, or you can ask whether something real happened, something so catastrophic, so deeply embedded in the human experience of living near water, that it refused to be forgotten. That is the question we are going to sit with tonight. Not whether a single miraculous flood covered every mountain on earth simultaneously. That is a theological question, and it belongs in a different conversation. What geology asks is something quieter and in some ways far more interesting. It asks whether there were real events, real floods, massive and terrifying and world-altering by any human measure, that could explain why so many people in so many places remembered water rising and a world being remade. And the answer geology is slowly uncovering is yes, probably more than one, possibly many. Here's what makes this such a compelling subject to explore. Geology can actually test these questions, not with certainty in every case, not with the clean finality of a laboratory experiment, but with evidence. Layers of sediment that record catastrophic inundation, coastlines that were drowned when ice sheets melted and sea levels climbed by hundreds of feet, lake basins that overflowed in single catastrophic events, river valleys so dramatically carved they look like the work of something barely imaginable. The Earth keeps records. It is not always easy to read them, and scientists disagree about the details more often than textbooks suggest, but the records are there. What geology cannot do is tell us exactly which flood inspired which story. That connection, the one between a real geological event and the specific cultural memory of a specific people, is harder to prove. It requires archaeology, linguistics, oral history, all of these fields working alongside the rocks and sediments. We will look at the evidence honestly, which means sitting comfortably with uncertainty, where uncertainty is real, and following the science where it leads. The guiding questions tonight are three. What actually happened? Where did these floods occur? And when? Because timing matters enormously. If a flood happened 2 million years ago, no human ancestor was likely there to remember it. But if it happened 12,000 years ago, or 8,000, or even 5,000 years ago, then the people living through it were, in many ways, people very much like us. They had language, they had storytelling, they had the capacity to pass something terrible and important down through generations, until it became myth, and myth became scripture. The timeline we will build tonight stretches from the end of the last ice age, roughly 20,000 years ago, through several thousand years of dramatic, sometimes violent planetary transformation, right up to the edge of recorded history. And along the way we will look at some of the most dramatic events this planet has produced in the memory of our species. An ice sheet the size of a continent melting into the sea. A freshwater lake the size of several modern nations breaking through its walls in a single catastrophic outburst. A shallow, fertile land between what is now Britain and continental Europe, swallowed slowly, then suddenly by the rising North Sea. A landlocked basin, possibly the origin of the Black Sea as we know it today, flooded by salt water rushing in from the Mediterranean. Each of these events is real. Each is supported by geological and oceanographic evidence, though scientists continue to debate the details, the scale, the pace. None of them require the supernatural. All of them are, on their own terms, almost beyond imagining. If you are using this to fall asleep tonight, that is exactly the kind of thing I hope settles gently into your mind as you drift off. Not anxiety, not urgency, just the quiet astonishment of realizing how much the Earth has been through, how much water has moved across its surface, how old these questions are, and how recently we have developed tools capable of beginning to answer them. Before we go any further, I want to ask you something. Drop a comment if you feel like it. Where are you listening from right now, and what time is it? I check these comments, and every single time they surprise me. Someone in New Zealand at sunrise. Someone in a rainy city in northern Germany at midnight. Someone in Texas who cannot sleep and has been listening for an hour already. There is something I genuinely love about that, about all of you scattered across the planet, lying in the dark or sitting quietly, turning over these old questions together. Tell me where you are, because that matters in a way that connects to tonight's subject more than it might seem. The people who lived through these ancient floods were also scattered across a changing world. They were also lying down at night beside rivers that were not the same rivers their grandparents had known. They were also asking questions about what happened and why and what it meant. The difference is that they did not have geology, they had memory. They had story, they had each other. Tonight, we get to bring both things into the same room. The stories and the stones, the myths and the meters of sediment. The question as old as rivers, and the science that is finally old enough and careful enough to start giving it real answers. So let's begin with what a flood story is actually made of, and why certain kinds of events produce the kinds of memories that last for thousands of years. Think about what a flood actually does to the people living through it. Not the numbers, not the cubic kilometers of water, but the human experience of it. One day you have a village. You have a well you know the depth of, a field you planted 3 weeks ago, a path worn smooth between your house and your neighbour's house. Then the water comes, and when it recedes, if it recedes, the path is gone. The field is buried under silt. The well is either destroyed or relocated by the new shape of the land. Everything that told you where you were in the world has been erased and replaced with something unfamiliar. If you survive that, you tell someone about it. You tell your children, they tell their children. And something of what happened persists, because the experience was too large and too disorienting to simply release. That is the raw material of a flood story. Not allegory, not invention, but the compressed memory of something that genuinely happened to people who had no other way to preserve it except language. Now, here is what makes flood traditions so fascinating and also so difficult to interpret. They appear on nearly every continent in cultures that had no contact with each other, and they share a recognizable structure. Rising waters that consume the known world. A warning received by someone who listens while others do not. A survivor, sometimes one person, sometimes a small group, who preserves life through the catastrophe. A world remade on the other side, different from what existed before. That pattern repeats in Mesopotamia and in the Pacific Islands, in the Amazon Basin and in the oral traditions of coastal peoples in southern India. You can read the Atrahasis epic, one of the oldest Mesopotamian flood texts we have, and then read a flood account from an indigenous people of the Pacific Northwest, and find structural echoes that seem almost impossible to dismiss. But here's the important question, and it is one that researchers genuinely argue about. Does that structural similarity mean these stories all trace back to a single catastrophic event? Or does it mean that the experience of catastrophic flooding is universal enough, and the psychological response to it consistent enough, that similar stories arise independently wherever people live in flood-prone landscapes? The honest answer is probably both, depending on which traditions you are comparing. Some stories may carry real memory. Oral traditions are more durable than people tend to assume. There is growing evidence, some of it quite recent, that extremely detailed geographical knowledge can survive in oral tradition for thousands of years. Researchers studying Aboriginal Australian traditions have found stories that appear to preserve accurate memory of sea level rise events from more than 10,000 years ago. Stories that describe specific bays and headlands that only existed before the coastline changed at the end of the last ice age. The geological record matches the stories. That is not nothing. That is a remarkable thing, and it suggests that in the right cultural conditions, with the right transmission practices, memory of actual events can persist across an almost unimaginable span of time. But oral tradition does not preserve events the way a security camera does. It transforms them. Every time a story passes from one generation to the next, it picks up new meaning, new emphasis, new elements that make it useful and relevant to the people telling it. A local flood that destroyed one community might grow in the retelling until it covers the known world, because the known world of that community was what mattered, and the flood had destroyed it completely in any experiential sense. A warning that one elder gave, perhaps a wise reading of weather signs or river behaviour, might become the voice of a god by the time the story has travelled 200 years. This is not deception. It is how meaning accumulates. It is how human beings make sense of events that otherwise resist comprehension. So what you end up with in most flood traditions is a layered thing. There may be a kernel of genuine memory at the centre, the fact of water rising, the loss of a familiar world, the survival of some and not others. Around that kernel there is interpretation, the attempt to explain why it happened, what it meant, what moral or spiritual lesson it carried. And around that there is adaptation, the way each generation reshaped the story to speak to its own concerns, its own relationships with gods and rulers and neighbours. By the time a flood tradition is written down, or recorded by an anthropologist, or studied by a geologist trying to find the event behind the myth, all three of those layers are present simultaneously, and they cannot be cleanly separated. This is why matching a specific story to a specific geological event is so much harder than it sounds. It is genuinely tempting when you find evidence of a catastrophic flood 8,000 years ago in the Black Sea region to say that event became the story in Genesis or the flood in Gilgamesh. But the connection requires more than temporal coincidence. It requires demonstrating that the people who experienced that event were the cultural ancestors of the people who told those stories, and that the story travelled with them, transformed but intact, across thousands of years and enormous distances. That chain of transmission is very hard to prove. Researchers try, and some make compelling cases, and others dispute those cases vigorously. We will look at several of those arguments tonight without pretending the debates are settled. What we can say with more confidence is this: there is no single flood behind the flood story. There is a category of experience, widespread, repeated across different times and places, that reliably produces this kind of memory. People living along rivers know floods. People living on coastlines know the sea's capacity to advance. In glaciated regions, people living downstream of ice-dammed lakes knew, at least occasionally, the terror of a catastrophic outburst that could reshape a valley in an afternoon. These were not rare exotic events. They were recurring features of life in a world that was, especially in the period between roughly 20,000 and 5,000 years ago, changing faster than at almost any other time in recent geological history. That period, the end of the last ice age and its long aftermath, is when the most dramatic large-scale events occurred. Sea levels rose by somewhere around 400 feet over several thousand years as the ice sheets melted. That rise was not smooth or gradual everywhere. Some coastlines were drowned slowly. Others experienced episodes of rapid inundation when massive ice sheets collapsed. Inland, ice-dammed lakes that had been accumulating meltwater for thousands of years gave way catastrophically, sending volumes of water downstream that defy easy comparison to anything in modern experience. Landscapes that had been home to people for generations disappeared underwater in timescales ranging from decades to single catastrophic days. This is the world in which the ancestors of every living human being were finding their footing. And it produced floods, many of them. Not one great flood, but a whole geological era of water moving in ways it had not moved before. Different events, in different places, at different times, experienced by different peoples who each had their own ways of understanding and preserving what they had witnessed. The motif of the Great Flood, then, might be understood not as a single memory, but as a kind of cultural sediment. Just as a river deposits layer upon layer of material carried from distant places and different times, the flood traditions of the world may represent the accumulated deposit of many real events, transformed and merged and given new meaning by the very human need to make a coherent story out of catastrophe. The specific details diverge. The deeper pattern persists. And the pattern persists because the experiences that generated it were real, and because water rising to destroy the familiar world is one of the most fundamentally destabilizing things that can happen to a community rooted in place. All of this is what we carry into the geological part of tonight's story. Not the expectation of finding one flood that explains everything, but the more interesting and more honest question of what actually happened, and where and when and whether the events that geology is uncovering are large enough and recent enough and well-placed enough to have made it into human memory at all. Some of them clearly are. Some are candidates that researchers are still actively investigating, and understanding what geology looks for when it reads the record of ancient floods, what signatures a catastrophic inundation actually leaves in stone and sediment, is the next piece we need before the larger picture can start to come into focus. To answer those questions, geologists have to do something very strange. They have to treat a landscape the way a linguist treats a text. Every hillside, every riverbank, every odd patch of sand on a cliff face becomes part of a sentence. The grammar is physics, the vocabulary is rock. When water moves, it leaves fingerprints. Not poetic fingerprints, but physical ones. Layers of sediment, scoured surfaces, oddly shaped hills and channels that do not match the slow work of ordinary rivers. If you know what to look for, you can walk through a valley and tell whether it has lived a quiet life, shaped by countless small floods and seasonal changes, or whether at some point it was hit by something far more violent. The first thing geologists pay attention to is sediment. The stuff a flood actually moves. Sand, gravel, boulders, silt, mud. In a normal river, that material is sorted. The smallest grains settle out in calm water, the coarser grains require stronger flow to move, and over time you get predictable patterns. Fine silts on floodplains, sands in point bars where the river curves, gravels and cobbles in the faster channels, the layers stack like files in a well-organized cabinet. A big, sudden flood is like someone grabbing that cabinet and shaking it. Catastrophic water flows can pick up boulders the size of cars and roll them along the bottom. They can peel up chunks of already hardened sediment and carry them away like rafts. Geologists call those chunks rip-up clasts, pieces of older layers that have been torn loose, transported, and then dropped into newer ones. Finding a layer of sand and gravel full of ripped-up fragments from the underlying bed is one of the classic signs that something very energetic happened there. The way the particles are arranged also matters. In a standard river flood, the water rises, carries a mix of grains, and as it slows, the heavier, coarser grains settle first, then the finer ones. This produces what's called graded bedding, a single layer that goes from coarser material at the bottom to finer at the top, sometimes repeated as a series of mini packages if the flow pulsed. Catastrophic floods can generate very thick, very dramatic graded beds, sometimes meters thick, recording a single event that started fiercely and then gradually lost power. Sorting is another clue. A deposit that is well sorted, where all the grains are roughly similar in size, suggests a more uniform flow regime. Poorly sorted layers where sand, pebbles and larger stones are jumbled together with little pattern can indicate rapid, chaotic transport, as you might expect in a dam break or sudden outburst flood. But sediment alone is not the whole story. Water moving at incredible speed also reshapes the solid ground. It cuts deep, streamlined channels instead of the meandering curves of a lazy river. It can carve long grooves in bedrock, scour out potholes, and leave behind steep-sided dry valleys that look far too large for the little streams that now occupy them. In some places it piles sediment into landforms that only really make sense if you imagine the entire valley filled with roiling, sediment-laden water. Geologists study these landforms as carefully as they study the grains. A landscape full of oversized channels, scoured bedrock, and oddly placed gravel bars high up on the valley walls is telling a story. Once, water levels here were far above anything seen in historical time. Of course, a story without a date is only half a story. To connect a physical flood deposit to human history, or even to other climate events, scientists need to know when it was laid down. That is where dating tools come in. For relatively recent floods, the last 50,000 years or so, radiocarbon dating is one of the main methods. It relies on the slow, predictable decay of radioactive carbon in once living material. If a flood buries a piece of wood or plant fragments or shells, those remains can be sampled. Measure how much radiocarbon is left, compare it to the known decay rate, and you get an age estimate for when that organism died and was entombed in the flood layer. Radiocarbon, though, has limits. It doesn't work well beyond a certain age, and sometimes there simply isn't enough organic material preserved. In those cases, geologists often turn to a technique with a slightly more mysterious name, optically stimulated luminescence, or OSL. Mineral grains like quartz and feldspar accumulate tiny amounts of energy from natural background radiation while they are buried and shielded from light. When those grains are exposed to sunlight, the stored clock is reset. When they are buried again, the clock starts ticking once more. In the lab, scientists can stimulate the grains with light, measure the energy they release, and estimate how long it has been since they were last exposed to daylight. That gives an age for when the sediment was finally laid down by water and covered. Another powerful time marker comes from the sky, not the river, tephra layers, the ash and pumice produced by volcanic eruptions. Large eruptions can spread distinct layers of ash over enormous areas. If a flood deposit contains a particular ash layer that has been independently dated, the flood must be younger than that layer. If the ash lies on top of the flood sediments, the flood must be older. In this way, tephra acts like a timestamp slipped into the geological record, allowing events in different places to be synchronized. Even with these tools, though, the answers are almost never precise calendar dates. Rocks do not come with April 14th, 7620 BCE stamped on them. Every method has uncertainties: contaminants in a radiocarbon sample, partial resetting of the luminescence clock, slight misidentification of an ash layer. When you see a flood dated to about 7,600 years ago, or between 13,000 and 11,500 years ago, that range is the honest expression of those uncertainties. It is not a weakness. It is the margin of error that comes from trying to read deep time through imperfect clues. There is another complication. Not all big water events are created equal. A huge river flood, a storm surge, and a tsunami can all leave sandy layers where there was once soil or vegetation. Distinguishing between them is a bit like forensic work. Tsunamis generated by earthquakes or landslides move in from the sea and then retreat. They often drag marine organisms inland and then back out again. Their deposits can show multiple sand layers in a single event, corresponding to successive waves, sometimes separated by thin veneers of mud or debris. The sand may contain tiny marine shells, foraminifera, or diatoms that lived in deep water, not in the shallow coastal zone. Storm surges from cyclones or hurricanes also bring the sea onto the land, but they tend to be more limited in height and reach than the biggest tsunamis, and they are accompanied by strong winds and rain. Their deposits often look different under the microscope, with more evidence of reworked beach material and less of the deep water signature that a tsunami can carry. River floods, in contrast, usually leave behind sediments that match the river's usual load, whatever that particular watershed tends to produce. They follow the path of the valley, not a straight push from the ocean. Their deposits climb the banks, spread across floodplains, and thin out with distance from the channel. If the source is glacial meltwater, you may see a lot of angular, freshly ground rock flour. If it is a dam break outburst, you may find those chaotic, poorly sorted gravels and conspicuous rip-up clasts. None of these criteria are perfect in isolation. Geologists rarely declare with absolute confidence that a given sand layer is definitely tsunami or definitely river based on a single feature. Instead, they build a case from multiple lines of evidence: sedimentology, microfossils, landform context, and the broader pattern up and down the coast or along the valley. Piece by piece, they reconstruct something that no one alive witnessed. A quiet hillside becomes a frozen moment in a violent event. A buried peat layer under a sheet of sand becomes the floor of someone's ancient world, drowned in a day. When you stack enough of those moments across a continent, and you date them as precisely as the tools allow, a larger pattern starts to appear. You begin to see not just isolated disasters, but episodes in which many rivers were high or many coasts were struck within a few centuries. You begin to see how flood stories might cluster around certain windows in time. And with that toolkit in mind, the fingerprints water leaves, the clocks hidden in grains of sand, the subtle differences between a river's rage and the sea's advance, we can finally step into the specific chapters of the last ice age and its long aftermath. Because the stage on which most of the world's great flood memories were likely set was not static at all. It was a world of ice, of melting, of seas on the move, and of rivers trying to adjust to a planet that was rapidly becoming something new. To understand why the Holocene is full of flood stories, you have to start with a world that barely resembles the one you know. A world in which the map of the continents was literally different. This was the time we call the last glacial maximum, roughly 20,000 years ago. Huge ice sheets smothered much of North America, Northern Europe, and Siberia. Mountains from the Andes to the Himalaya wore heavy white crowns. And all of that ice was made of water that used to be in the oceans. Sea level was not just a little lower, it was about 120 meters lower than today, give or take. That is the height of a 40-story building shaved off the surface of every ocean on Earth. When you pull that much water out of the sea, something dramatic happens. The edges of the continents, the broad, shallow shelves that modern maps colour as ocean, rise into the air. Coastlines march outward, sometimes tens or even hundreds of kilometres. Places that are now seabed become dry land. Plains, river valleys, estuaries, and wide marshy lowlands. If you could walk around the world at the last glacial maximum, you would see an unfamiliar geography. Britain was not an island, but the northwest corner of a broad landmass connected to Europe. Siberia and Alaska were joined by a region we now call Beringia, a cold but habitable bridge between Asia and the Americas. Southeast Asia was welded into a single subcontinent by the exposed Sunda Shelf. The Persian Gulf was mostly dry land. Vast tracts of what is now the North Sea, the Yellow Sea, the Arafura Sea, the Java Sea were windswept plains or braided river deltas. These were not just blank spaces, they were habitable. In many cases, they were some of the best real estate on the planet. Shallow continental shelves tend to collect rich sediments. Rivers deliver nutrients. Sunlight penetrates easily. In a cooler, drier glacial climate, the new coastal plains and river valleys on these shelves would have offered fresh water, abundant plant life, and migrating herds. In temperate latitudes, they were likely milder than the interior, buffered by the nearby ocean. For hunter-gatherers, that combination is magnetic. Human groups, wherever they were in the world, tended to drift toward these productive edges. River mouths, lagoons, narrow coastal strips where land and sea met in a tangle of resources. At the last glacial maximum, and during the long cold millennia around it, many of the world's most attractive living spaces were not where our coasts are today. They lay far out, on ground that is now under tens of meters of water. That is the stage. Now imagine the mechanism behind it. An ice sheet is not just a pretty white blanket, it is a planetary savings account for water. When snow falls on a continent and does not melt in summer, when year after year more snow is added than removed, that snow compresses into ice. Over thousands of years, ice sheets can grow kilometers thick. Every cubic kilometer of ice is a cubic kilometer of liquid water that has been locked away from the ocean. As long as the Earth stays cold enough, that account grows. When the climate warms, the balance tips the other way. Ice does not melt politely. It does not simply shrink a little each year like frost on a window. As temperatures rise, ice sheets develop meltwater channels on their surfaces, lakes at their bases, and long hidden rivers that lubricate their contact with the ground. Their edges become riddled with fractures and crevasses. Huge tongues of ice reach out into the sea, forming floating shelves that can suddenly break apart. Some melt is slow and steady, vast areas oozing more water each summer than the last. But other parts are punctuated by sudden releases. Ice-dammed lakes drain catastrophically. Glaciers surge. Ice margins retreat in big jumps when an ice shelf collapses and no longer buttresses the ice behind it. From the ocean's point of view, all of this shows up as rising water. On geological timescales, the transition from the last glacial maximum to a warmer world was extraordinarily rapid. Over roughly 10,000 years, global sea level rose those 100+ meters, but the rise was not smooth. It came in pulses. Geologists call the most dramatic of these episodes meltwater pulses. They show up in coral reefs that grew near the sea surface and then were drowned, in submerged shorelines, in the chemistry of marine sediments. During some of these pulses, sea level may have climbed by several meters in just a few centuries, perhaps even faster during the steepest parts of the curve. If you lived on one of those exposed coastal plains, you would not notice the ocean lurching skyward in a single lifetime. Year to year the change would be subtle, a few millimeters, perhaps a couple of centimeters in a bad decade. But that slow, inexorable rise does not act on a flat world. A gently sloping coastal plain can extend for tens of kilometers at very low elevation. Raise sea level by 1 meter, and the shoreline might move inland 100 meters in some places, or a kilometer in others. Do that again and again, and over a few hundred years, the sea can invade what used to be dry land for the distance of a day's walk. Add storms, high tides, and occasional extreme events, and the experience is not gentle at all. Salt water pushes up rivers, poisoning fields and freshwater marshes. Barrier islands migrate landward. Storm surges reach farther each generation, chewing away at dunes and bluffs that people assumed were solid. Wetlands and lagoons overrun older campsites and burial grounds. A village that felt safely inland when a grandparent was born may suddenly find itself on the front line of the sea. Now layer in the fact that humans were not evenly scattered across the planet. They clustered in those rich lowlands along rivers, in estuaries, on deltas, exactly the places that suffer most when sea level rises. This is where the geological story and the human story collide in a way that complicates our evidence. The best early Holocene settlements, the ones with abundant food, stable water, and easy travel routes, were often on coasts that no longer exist. They have been drowned. Where modern coasts are steep and rocky, we can sometimes find ancient shorelines, caves with old occupation layers, terraces that record former sea levels. But on broad continental shelves, the archaeological record has simply been pushed out beyond the reach of casual discovery. Tools, hearths, middens, perhaps even early experiments with cultivation and animal management, are now buried in marine mud. This means our picture of human life during the crucial window, when many flood stories may have formed, is systematically biased. We see the inland camps, the highland refuges, the places people occupied when they had to retreat. We see much less of the low-lying worlds they lost. From a storytelling perspective, those losses would have been powerful. As sea level rose through the late glacial and into the early Holocene, the same basic drama played out again and again around the globe. Coastlines redrew themselves, rivers shifted course as their mouths drowned, and their gradients changed. Estuaries widened. Some valleys became long, narrow bays. Others turned into island chains. Groups living in different regions would not have shared the details. The plants, animals, and exact topography varied from place to place. But the broad themes were repeatable. Water where there used to be land. Old paths cut off. Ancestral sites swallowed by the sea. Families forced to move upslope, sometimes into territories already occupied by others. Meltwater pulses turned slow background change into episodes that felt sharper. A few generations might witness coastlines advancing unusually fast, storms biting deeper, rivers behaving in new and unsettling ways. Oral traditions do not need precise dates. They need drama. The sea has always eaten the shore makes a poor story. In your great-grandfather's time, the sea came farther in a single lifetime than it ever had before, is different. Once people began to settle more densely to experiment with proto-agriculture, to anchor their identity to specific places rather than flexible ranges, these changes would have cut even deeper. The early Holocene is exactly when that transition is unfolding in many parts of the world, after the big ice sheets have begun to retreat, but while sea level is still rising fast and rivers are still adjusting to a new base level. It is in that unsettled interval that a local flood can become more than a local memory. Coastal groups displaced by rising water carry their stories inland. Traders share accounts of drowned lands with people who have never seen the sea. Myths about a world reshaped by water begin to circulate through networks that are becoming wider and more complex. By the time sea level approaches something like its modern position, around 6,000 or 7,000 years ago, humanity is living in a world whose coastlines have been on the move for millennia. The Ice Age has ended, but its aftershocks are everywhere, in the drowned shelves that hide ancient camps, in the changed rivers, and quite possibly in the stories people tell about a time when the boundaries between land and water were anything but fixed. With that backdrop of shifting seas and vanishing coastlines in mind, we can turn from the global to the particular, the concrete ways in which rising water and glacial melt rearranged specific parts of the map, and how those rearrangements might underlie some of the most persistent flood legends we know. When geologists talk about rapid sea level rise, they mean something very different from what you or I would feel standing on a beach. On a graph spanning hundreds of thousands of years, the curve at the end of the last ice age looks like a rocket launch, 120 meters in roughly 10,000 years. On average, that's a little over a centimeter per year. During the steepest meltwater pulses, global sea level may have climbed 2 or even 3 centimeters a year for a few centuries at a stretch. 2 centimeters, less than the thickness of your finger. If you lived on a rocky cliff coast, you might never notice. But if you lived on one of those broad, low-lying plains that had been exposed at the glacial low stand, the impact was not abstract. The world beneath your feet literally changed shape within the span of remembered ancestors. Imagine a coastal plain with a slope so gentle, you barely feel it. Each metre of vertical rise might push the shoreline inland 50 metres, or 100 or more. Now imagine that over 2 or 3 human lifetimes the water creeps in by several metres. Hills become peninsulas. Peninsulas become islands. Shallow valleys turn into estuaries, then bays, then drowned fjords. What looks to a geologist like a smooth line on a chart looks to the people living through it like a series of thresholds. At first you might just lose the farthest hunting grounds, the outer marsh where the shellfish beds are most abundant. Then one year a storm coincides with an unusually high tide and water surges into places it has never reached before. The path to the neighbouring group's camp is cut for a few days. A burial ground on the low ridge above the river floods for the first time anyone can remember. Elders say the ancestors never saw this. Children grow up being told that the sea is behaving strangely. A generation later, that strange behaviour is normal, and the new strange is farther inland still. As the sea moves, people have to move with it. And movement, especially in a world that is already occupied, is rarely peaceful and uncomplicated. Some groups have room to back away from the rising water. Their territories extend into higher ground, or the neighbours are distant enough that everyone can shift upslope without much friction. Others are hemmed in by mountains, by ice, by deserts, or simply by other people who do not want to yield the only good land left. Rising seas can turn a flexible, mobile lifestyle into a forced march. Camps that once were seasonal stopovers become permanent refuges. Places that were peripheral become central. New trade routes open where rivers have become navigable estuaries. Old ones close when sandbars shift, when crossings drown, when headlands become dangerous. Wherever different groups' retreat paths intersect, you have the ingredients for tension. Archaeological layers from the early Holocene in some regions show hints of this. Fortified settlements appearing along river valleys, changes in tool types that may reflect new neighbours, sudden abandonments of low-lying sites, followed by denser occupation upslope. It is rarely possible to say this conflict began because of sea level rise. Human motives are tangled, but when you look at the timing, you often see social reorganization shadowing the lines of the rising ocean. From the perspective of culture, losing land is not just an economic problem. It is an identity problem. Sacred groves, burial mounds, rock art sites, particular bends in a river associated with origin stories, these are not easily replaced. When the tide begins to lap at a place your stories say was fixed at the creation of the world, you do not simply redraw the map in your head. You argue with your own cosmology. Sometimes cultures respond by adjusting the myths. The sea is angry, or the gods are cleansing the world, or some primordial boundary has been broken. Sometimes the stories record the loss more directly. There was once a forest here. Our ancestors walked where fish now swim. The old village lies under the waves. Geology gives us independent evidence that such claims are not just poetic. On many modern coasts, divers and sonar have found submerged forests, stumps and trunks of trees still rooted in ancient soils now lying below high tide. In some places, the wood is so well preserved you can see the growth rings. Radiocarbon dating shows that many of these forests were alive 8, 9, 10,000 years ago during the main phase of post-glacial sea level rise. Elsewhere, cores drilled beneath harbours and estuaries bring up layers of peat, compressed remains of reeds, mosses and other marsh plants, sandwiched beneath marine mud. Those peats formed in freshwater or slightly brackish wetlands at or just above sea level. The marine sediments above them record the invasion of the sea. You can read the story in cross-section. At the bottom, coarse river gravels and sands, a valley floor. Above that, peat and marsh deposits, a river mouth or coastal wetland. Above that, fine silts and clays full of marine shells, an estuary or bay. Sometimes, higher still, you find younger peats again, marking the later growth of salt marshes on the new shoreline. In many places, the valleys themselves are still recognizable, only now they are drowned. Sail into a long, narrow inlet on a fjord coast or a ria, and you are gliding over what was once a river valley. The shape of the land is the same. The water has simply climbed the walls. Sonar mapping of continental shelves reveals entire networks of these submerged valleys. They branch and meander exactly like rivers on land, then stop abruptly at what used to be the glacial age coastline, now far offshore. It is not difficult to imagine that people once followed those rivers, camped on their banks, and watched as the ocean slowly pushed upstream, step by step, century by century. All of this evidence tells us that global sea level rise after the last ice age was very real and very large. But its effects were never uniform. Ice sheets do not melt evenly. Land, freed from the weight of ice, rebounds upward. Gravity itself is distorted by the mass of the ice, drawing ocean water toward it. When the ice disappears, that gravitational pull weakens and water redistributes. Local winds, currents and tides amplify or dampen the changes. The result is a patchwork. While global average sea level was rising, some coasts experienced much faster relative rise, others stayed nearly stable for long intervals, or even saw the sea fall as the land bobbed up. A village on one stretch of shoreline might see its harbour deepen and its fields drown within a few lifetimes, while a community a few 100 kilometres away might notice only modest changes. From a scientific viewpoint, this is a matter of isostatic adjustment and regional sea level curves. From a human viewpoint, it means that the Great Flood was never a single synchronous planet-wide wave. Instead, over thousands of years there were countless local and regional Great Floods. A bay that did not exist when grandparents were young. A land bridge that vanished within 3 or 4 generations. A lagoon that turned first to marsh, then to open sea. Each of these events would have felt absolute to the people affected. Their whole known world of land and water had shifted. Some of those communities moved inland and told their neighbours what had happened. That the sea had risen, that the coast had been devoured, that forests had become fishing grounds. As those stories travelled, they could be combined, embellished, universalized. A flood here, a flood there, a drowned valley in this generation, and a lost island 3 centuries later, all folded over time into narratives about a time when the waters came up and remade the earth. In other words, before we even get to sudden outburst floods and catastrophic dam failures, the simple, relentless rise of the post-glacial oceans was enough to seed the world with flood memories. What glaciers did in an eye blink of geological time-shaped coastlines moved people and filled human imaginations with the idea that the boundary between land and sea is neither permanent nor safe. To see how those ideas might have crystallized around particular dramas, we need to look away from the slow creep of the tide and toward the moments when water did not merely advance, but surged, when lakes failed, ice dams broke, and rivers themselves briefly behaved like seas. When an ice sheet grows big enough, it does not just sit politely on top of a continent. It slumps, buckles, and sags into the landscape. It blocks valleys that rivers used to follow, dams basins that once drained freely to the sea, and leaves behind enormous hollows where meltwater can collect. Put ice across a river mouth, and you have built a dam. Put tens of meters, hundreds of meters of ice there, and you have built a very strange kind of dam, one that looks solid, but is constantly deforming, cracking, melting from below. Behind those frozen walls, meltwater accumulates. glacial lakes can reach sizes that are hard to grasp from modern experience. Picture a lake stretched along the front of a retreating ice margin, hundreds of kilometers long, sitting where today you might see a broad plain or a chain of smaller lakes and bogs. In North America, after the last ice age, there were several of these giants, Lake Agassiz, Lake Ojibwe, Lake Missoula, and others, each holding more fresh water than all the Great Lakes combined at certain times. In Eurasia there were equivalents, vast lakes ponded south of the Scandinavian ice sheet, in the basins of Siberian rivers, in the valleys of the Altai and Tian Shan. Maps of the late glacial period look almost unreal, with pale blue patches sprawled across interior continents, pressed up against white sheets of ice. An engineer looking at these systems would ask a simple question: how stable is that dam? The answer, in geological terms, is not very. Ice is strong enough to hold back water for a while, but it is not rock. It flows under its own weight. It fractures along internal weaknesses. It floats when the water behind it becomes deep enough. Warm water can tunnel underneath it, carving sinuous passages that grow and merge. As long as the water level stays within certain bounds, the system can remain in a sort of uneasy balance. The lake fills in summer, drains a bit through subglacial tunnels, then refreezes or stabilizes in winter. But if the water rises too high, or if the plumbing beneath the ice becomes too efficient, the balance breaks. Dams fail. When an ice dam breaks, it does not crumble grain by grain like an earthen embankment. It can lift, shatter, and disintegrate in a matter of hours or days. The lake behind it, thousands of cubic kilometers of water, suddenly has a path to lower ground. This is what glaciologists call a jökulhlaup in Icelandic, or more generally a glacial outburst flood. The word sounds exotic, but the physics is simple. Once a large body of water finds a steep enough slope and a wide enough opening, the flow rate increases, the channel erodes, the opening widens, and the system runs away. Discharge can reach tens of millions of cubic meters per second, orders of magnitude larger than any ordinary river. In those moments, a valley ceases to be a river valley and becomes a temporary sea. Water roars down, dragging ice blocks the size of houses, boulders the size of cars, whole forests ripped from their roots. It scours soil to bedrock. It plucks blocks from fractured rock surfaces. It pours over divides into neighbouring basins, carving new spillways that remain as dry passes long after the flood has gone. When geologists walk these landscapes today, they see signatures that ordinary river processes struggle to explain. You find boulder bars, ridges and mounds of stones and cobbles piled in arcs across valley floors, too coarse and too high to have been abandoned by a meandering stream. You find streamlined hills, what in the Columbia Plateau of North America are called scablands, where the topsoil has been stripped and the underlying basalt sculpted into smooth, elongated forms pointing downstream. You find spillways, broad, flat-bottomed channels cut right through bedrock divides, with no modern river big enough to justify their size. Sometimes they lead from one basin to another with a neat logic. Here is the former glacial lake. Here is the notch in the rim where the lake finally found a lower outlet. Here is the enormous dry channel that carried the flood. In some places, you even find giant current ripples, so large that you can walk across them without realizing what they are. These are not the delicate ripples you see in sand at the beach, but hills of gravel and sand tens of meters apart and several meters high, arranged in parallel ridges across a former lakebed or floodplain. Their spacing matches what hydraulic theory predicts for water hundreds of meters deep, moving at highway speeds. This is the expected evidence of an outburst flood. Oversized landforms that only make sense if water was, for a brief time, flowing far faster and far deeper than anything we see in modern rivers. The timing of these events clusters around the end of the last ice age, between roughly 20,000 and 8,000 years ago. but they are not all synchronized. Lake Missoula's repeated floods into what is now Washington state seem to have occurred dozens of times between about 18,000 and 13,000 years ago. The catastrophic drainage of Lake Agassiz Ojibwe, which may have freshened the North Atlantic and disturbed climate, likely happened closer to 8,200 years ago. In Eurasia, outburst floods from proglacial lakes along the margins of the Scandinavian ice sheet sent surges down the Baltic Basin into the North Sea, and along the great rivers of Siberia at various times during the same broad window. Individual Jökullaups from mountain glaciers in Iceland, the Alps, the Caucasus, and Central Asia punctuated the deglaciation with smaller but still dramatic local floods. There is no single global date you can point to and declare, this is when the world was flooded. Instead, the late glacial and early Holocene were dotted with these catastrophes, each one regionally immense, each one short-lived in geological terms, but potentially unforgettable to the people close enough to see it. Imagine you're living downstream of one of these ice-dammed lakes. For generations there is simply a large river, perhaps prone to seasonal variability, but bounded by familiar banks and terraces. Upstream, beyond the tongue of ice, there is talk of a great inland sea, but it is out of sight, behind dangerous country. Then one year, without warning in any human timescale, the dam goes. The first sign may be a distant roar that does not stop. Then the river begins to rise, not inches over days, but meters over hours. Whole groves vanish. Low hills become islands and then are gone. The water carries icebergs and tree trunks and dead animals. It carries houses, granaries, camps. If you survive and struggle to high ground, you will watch an entire valley change in a day. After the water drains, the old floodplain is stripped, rearranged, armoured with stones. Familiar paths do not exist anymore. Fishing spots, fords, burial places, all are gone. From a human vantage point, that is not a regional hydrological event. It is a world-ending flood. Crucially, many of these basins lay within reach of late glacial and early Holocene peoples. The Missoula floods poured across parts of what is now the Pacific Northwest, an area that shows evidence of human presence by at least 16,000 years ago and likely earlier. The margins of Lake Agassiz nibbled at lands used by Paleo-Indian groups in central North America. In Eurasia, communities hunting along the periphery of the Scandinavian ice sheet or following reindeer herds across Siberia would have been living in landscapes repeatedly reworked by glacial lakes and their occasional escapes. Some floods may have caught people unawares. Others may have been preceded by subtle signs, creaking and booming from the ice dam, rising groundwater in lowlands, strange behaviour of the river. Either way, the aftermath would have been the same: displacement, loss, the need to explain how stable valleys could be erased almost overnight. When later generations remembered such events, they would not have spoken in terms of specific lakes and discharge rates. They would have told of a time when the waters trapped against the ice broke free and swept away everything that stood in their path. They might have placed that story in a mythic past, or tied it to moral lessons about human behaviour, or blended it with memories of other floods, storm surges, tsunamis, rising seas. From the perspective of geology, these ice dam failures were scattered episodes, separated by thousands of kilometres and often thousands of years. From the perspective of oral tradition, they form a pattern, the idea that water held back can one day rush out, that the solid things in the world, valleys, rivers, even mountains, can be overturned without warning. In the next section, when we focus in on one of the best studied examples, the Missoula floods and the channeled scablands, we will see in fine detail how geologists reconstructed such a story from the rocks alone, and why some of the earliest scientists to suggest it were mocked for believing in a flood big enough to remake a landscape. The story starts with a lake that no one alive has ever seen. If you stand today in western Montana, near the town of Missoula, you see a long valley with a modest river. Some farms, a college town. The hillsides are dotted with houses and forests. Nothing about it screams ancient inland sea. But if you look carefully at those hills, you notice something odd. The slopes are marked by horizontal lines, benches and terraces that wrap around the valley like bathtub rings. They sit at different heights, one above another, as if a giant had filled the valley with water again and again, each time to a slightly different level. Those are exactly what they are, ancient shorelines. During the last ice age, a lobe of the Cordilleran ice sheet crept down the valley of the Clark Fork River, near the present border of Idaho and Montana. Where it crossed the valley, it acted as a plug. Ice hundreds of meters thick slumped across the river's course, blocking the outlet. Behind that wall, water rose. Lake Missoula was not a pretty blue lake tucked between a few ridges. At its maximum, it stretched more than 500 kilometers across western Montana. It filled multiple valleys. It drowned entire towns' worth of modern topography. At high stand, it held on the order of 2,000 cubic kilometers of water, more than the volume of Lake Ontario, Lake Erie, and Lake Huron combined. As the lake rose, the ice dam thickened and adjusted. The two systems, the rising water and the flowing ice, pushed against each other in a delicate, unstable balance. For a while the dam held. Leaks tunneled under it. Some water escaped through subglacial plumbing. Winter slowed the seepage. Summer melt added more. Then, at irregular intervals, the balance failed. At some point, the water in Lake Missoula became deep enough that the floating forces on the dam exceeded the friction holding it in place. Or warm water cut a tunnel under the ice that grew too quickly to be stabilized. The dam began to lift or shatter or tear open along weaknesses. Once a large enough passage formed, the flood was inevitable. The lake did not drain over a season. It dropped hundreds of meters in a matter of days. Out of the gap at the Idaho-Montana border, a wall of water surged west. At peak discharge, estimates suggest the flow rivaled all of the world's present rivers combined. Water hundreds of meters deep and moving at freeway speeds thundered through what is now the Clark Fork, then down the Spokane and Columbia basins, racing toward the Pacific. Along the way, it did surgery on the landscape. Look at eastern Washington today and you find the scars. Vast tracts of the Columbia Plateau are stripped to bare basalt, the soil and weathered rock peeled off like old paint. The basalt itself is carved into streamlined hills and grooves, all aligned with the direction of flow. Between them lie deep rock-cut channels, coulees with flat floors, and near vertical walls, far larger than any modern river would need. You see giant cataract systems like dry falls, a cliff several times wider than Niagara, with plunge pools at its base carved into the rock, standing today as a dry semicircle in the middle of an arid plateau. There is no modern river there that could possibly have created such a feature. You find bar after bar of boulders and cobbles heaped tens of meters high across valley floors. And in the Pasco Basin and along the lower Columbia, you find those giant current ripples, gravel hills spaced like ocean waves but solid, frozen proof that water once flowed here in volumes that defy everyday experience. When early geologists in the Pacific Northwest started to suggest that these landforms were the result of a single or a few enormous floods, their colleagues were not impressed. The scientific mood in the late 19th and early 20th centuries was strongly uniformitarian. The idea that the present is the key to the past, and that slow, continuous processes, ordinary rivers, ordinary erosion, could explain most features in the landscape if given enough time. Catastrophes, especially floods, sounded uncomfortably close to biblical stories. Into this environment stepped a geologist named J. Harlan Bretz. In the 1920s, Bretz walked the channeled Scablands. He mapped the coulees, the dry cataracts, the streamlined hills. He saw the scale of erosion, the evidence of flow directions, the absence of any modern rivers capable of doing this work. He concluded that only a catastrophic flood could have carved the terrain. His peers pushed back hard. They suggested alternative explanations. Perhaps the Scablands were carved slowly by glacial meltwater streams over tens of thousands of years. Perhaps they were the work of ice, not water. Perhaps Bretz had simply overestimated the scale of the problem. For decades, the Spokane flood hypothesis, as it was sometimes called, sat at the edge of respectability. The turning point came when another geologist, Joseph Pardee, documented the shorelines and other features of the ancient Lake Missoula Basin in Montana and recognized evidence of enormous currents there as well, giant ripples on what had been the lake floor. He estimated how much water the lake had held. He showed that its sudden release could, in principle, feed the kind of flood Bretz required. Gradually, more data accumulated. Better maps tied the scablands back to the outlet where the Clark Fork had once been plugged by ice. Sediment dating constrained the timing, and something else became clear. Not only had there been one flood, there had been many. The multiple shorelines around Missoula pointed to repeated filling and draining of the lake. Loess and soil layers between flood deposits in the Columbia Basin suggested long quiet intervals between high-energy events. The consensus that emerged over the late 20th century was not of a single unimaginable deluge, but of a sequence of perhaps 40 to 80 Missoula floods occurring over several thousand years between roughly 18,000 and 13,000 years ago. Each flood lasted only days to weeks at peak intensity. Each one roared across the same general path, reoccupying channels gouged by its predecessors, deepening them, widening them, stripping away whatever sediments and vegetation had recovered in the meantime. From the perspective of the landscape, this repetition matters. A single flood can do impressive work, but multiple floods, each piggybacking on the last, can create features of almost impossible scale. A coulee that looks too big for one event might be exactly what you expect from dozens of catastrophic pulses. A dry waterfall that dwarfs Niagara may be the cumulative product of floods spread over centuries. This is how repeated regional catastrophes can generate terrains that, at first glance, seem to demand a global one. In the end, the Missoula flood story triumphed, not because it was dramatic, but because it accounted for the evidence more cleanly than slow and steady alternatives. Hydraulic calculations match the size and spacing of giant ripples. Erosion modelling supports the need for deep, fast flows. Dating of flood deposits lines up with the presence and disappearance of the ice dam. There are still details under debate: exactly how many floods occurred, the precise volumes and peak discharges, whether some events were much larger than others. The broad picture, though, that ice-dammed Lake Missoula filled and catastrophically drained many times near the end of the last ice age, is one of the most secure pieces of quaternary geology. What does this mean for flood traditions? It shows that human-scale worlds can be destroyed by water in ways that leave permanent marks on the land. It shows that a valley or plateau can be reworked so thoroughly that later inhabitants, seeing only the aftermath, might reach for stories of a time when the waters rose to the mountains. It demonstrates that catastrophic floods are not myth in principle. They are part of Earth's recent history. But it also shows limits. The Missoula floods were immense, yet they were confined to the Pacific Northwest and the lower Columbia. They did not wash over Europe or the Middle East or Australia. Their timing falls within a window when people likely lived in or near the affected region, but they cannot alone account for flood stories from Mesopotamia, India, China, or the Mediterranean. They are instead one powerful example in a wider pattern: glacial lakes failing, coastlines drowning, rivers jumping their banks on a scale that matters to human memory. To see how these regional cataclysms might connect, or fail to connect, with ancient narratives from other parts of the world, we need to leave North America and cross the Atlantic, to a stretch of shallow continental shelf that during the Ice Age was not sea at all but dry land. When you look at a map of Europe today, the North Sea seems like a simple boundary. water between Britain and Scandinavia, fishing grounds, ferries, offshore wind farms and oil rigs. But during the last ice age, and for thousands of years after the ice began to melt, that sea was not a sea at all. It was a landscape. Stretch a mental skin across the shallow waters from the east coast of England to Denmark, the Netherlands and southern Norway, and you begin to see it. A low, rolling plain braided with rivers, marshes and lakes. Dry steppe in colder times. Then, as the climate warmed, a patchwork of grassland, forest and wetland. This drowned country has a name now, Doggerland. The word comes from the Dogger Bank, a shallow shoal in the central North Sea, long known to sailors and fishers. For most of human history, nobody suspected it was just the crest of a much larger submerged plateau, a remnant of land that once tied Britain to the continent. During the glacial maximum, sea level worldwide stood more than 100 metres lower than it does now. So much water was locked up in ice that coastlines were displaced far out on the continental shelves. In the North Sea basin, what is now ocean floor lay exposed to the sky. People almost certainly lived there. They would not have called it Doggerland, of course. To them it was simply the world, a place of seasonal migration routes, reindeer or red deer herds, rivers full of fish, sheltered spots for camp after camp, generation after generation. Archaeologists working along the modern coasts have found the edges of that world. Mesolithic tools and hearths on what are now tidal flats. Peat deposits with footprints and trackways cut by people and animals moving between forest and shore. And, pulled up accidentally by trawlers from the seabed, flint points, worked bone, even fragments of human and animal skeletons, that, when dated, fall into that window after the ice but before the sea. All of it points to a simple conclusion. The North Sea used to be a lived-in landscape. The way it disappeared matters. Doggerland did not vanish in a single night of roaring water. It drowned stepwise over millennia, as global sea level rose in response to retreating ice sheets. Imagine living there across generations. In your grandparents' stories, the coast was miles further out. The old hunting ground beyond the marsh is now open water. There's a favourite oak that used to stand on dry soil by your childhood. It grows at the edge of a brackish inlet. By your old age its dead trunk sticks out above a tidal channel. You can adapt to that for a while. Move camp a little inland. Build differently. Shift where you fish, where you collect reeds, where you bury your dead. But stepwise does not mean gentle. Sea level rise after the ice age was not perfectly smooth. It was punctuated by episodes when ice sheets dumped enormous volumes of meltwater into the oceans over relatively short timescales. A coastline might creep inland for centuries, then jump dramatically over a few human lifetimes. In low-lying terrain like Doggerland, each jump would have been brutal. Whole river valleys turning to estuaries, marshes swallowing forests, salty fingers pushing far up freshwater channels, places that had been safe for centuries becoming uninhabitable within a few generations. And then, on top of that long-term drowning, came something more sudden. Around 8,200 years ago, off the coast of what is now Norway, a huge section of continental slope failed. Sediments that had been stacked and oversteepened along the edge of the shelf collapsed and slid downslope in a submarine landslide, now called the Storegga Slide. When so much material moves that quickly underwater, it pushes the sea itself out of the way. The result was a tsunami. Modelling and sediment evidence suggest that this Storegga tsunami raced across the North Atlantic and slammed into coasts from Norway to Scotland to the Shetlands and the eastern side of what is now Britain. Run-up heights probably varied widely depending on local topography, but in some embayments and low coasts, waves may have reached tens of metres high, and in between those coasts, stretched across the shallow banks that were already under pressure from rising seas, lay the last fragments of Doggerland, Reconstructing exactly how much land remained habitable in the North Sea basin at the time of the Storegga event is difficult. By 8,200 years ago, a lot of Doggerland was probably already estuary, shoal and lagoon. But a lot is not all. Many reconstructions show residual islands, peninsulas and low plains still above water, prime real estate for Mesolithic communities following rivers and coastlines. For people on those lowlands, the tsunami would not have been an abstract geophysical event. It would have been a wall of moving sea. You wake to the usual sound of wind and birds. The tide has its normal rhythm. Then, inexplicably, the water pulls back, exposing ground no one has ever seen dry. Fish flopping in the shallows. People shouting puzzled. And then an advancing roar. A wave powerful enough to strip soils, uproot trees, and rearrange sandbars does not have to be hundreds of meters high. In a flat country barely above the level of a high spring tide, even a few meters of fast-moving water can sweep far inland, smash huts, and scatter communities. What makes the Storegga tsunami extraordinary in this context is not that it single-handedly created the North Sea. It did not. But it arrived in the middle of a long process of drowning. If your world has already been shrinking for centuries, if old campsites are underwater and the graves of your ancestors lie under tidal creeks, then one day the sea rushes in far beyond anything anyone can remember, carrying salt into fresh water, cutting off familiar paths, erasing landmarks. How does that feel? From the perspective of the people living through it, the combination of gradual sea level rise and sudden, violent inundation could easily have the flavour of a world-ending flood. Not a planet-wide ocean, but a personal apocalypse. Your bay, your river, your low island, gone. The safe places, no longer safe. The line between land and sea, no longer trustworthy. For geology, the Storegga event is recorded in layers of sand and disturbed peats along modern coasts. For archaeology, it sits at the edge of a frustrating problem. Most of the places where Mesolithic communities actually lived in Doggerland are now under tens of meters of water and sediment. The camps, the middens, the hearths that would tell us how they reacted to encroaching seas and sudden waves are difficult and expensive to find. We catch only hints, a worked antler dredged from the seabed, a cluster of tools preserved in peat, a scattering of bones eroding from a submerged channel. These fragments suggest continuity and disruption side by side. People did not simply vanish when the waters rose. They moved to higher ground, to the emerging coasts of what would become Britain and the Low Countries. They carried their skills and stories with them. But what exactly they remembered, what stories they told on dark nights about the time the sea came in and never quite went back out, we can only guess. Doggerland, like Lake Missoula's Scablands, shows us that a flood is often not one event, but the intersection of different kinds of change, slow, relentless background rise, punctuated by abrupt disasters. To see how another such intersection might have played out in a different corner of the old world imagination, we need to turn southeast, to another semi-enclosed basin whose shores have hosted human societies for a very long time, the Black Sea. When people talk about great floods and ancient memory, this is often where they land, the Black Sea. Pull back from a modern map for a moment and look at it not as a blue patch next to Turkey and Ukraine, but as a basin at the edge of two worlds, the Mediterranean to the south and west, the broad plains of Eurasia to the north and east, and, just over a shortland bridge, the Near East, the cradle of some of the earliest farming villages, and, eventually, the literate cultures that wrote down stories of catastrophic floods. The Black Sea flooding hypothesis grew out of a simple but dramatic idea. At the end of the Ice Age, global sea level was much lower than today. The Mediterranean sat lower too. The Black Sea basin, which is deeper and more enclosed, may have been cut off from the Mediterranean entirely, fed only by rivers like the Danube, Dniester, and Dnieper. In that scenario, it would have been a large, mostly freshwater lake with shorelines far below the modern coasts of Bulgaria, Romania, and Turkey. As the ice melted and global sea level rose, the Mediterranean climbed as well, creeping up toward a narrow sill where modern Istanbul straddles Europe and Asia. At some point, the argument goes, Mediterranean water finally overtopped that barrier. Once the sill was breached, gravity would have done the rest. Salt water would have poured north into the lower Black Sea basin, like a tap suddenly turned on. The rising surface would have chased the old freshwater shoreline upslope, drowning river valleys, low plains, and any human settlements that occupied them. In its more dramatic versions, the hypothesis imagines a roaring, almost Niagara-like cascade at the Bosporus, feeding a fast-rising inland sea that could have climbed tens of meters in a human lifetime. If you were farming or fishing along that ancient lake, watching the waterline surge inland year after year, the sense of a world overtaken by the sea would have been hard to miss. How do you test something like this without a time machine? Geologists look to the margins of the basin, those gentle underwater slopes where ancient shorelines, if they existed, might have left their marks. Repeated surveys of the Black Sea floor have mapped a series of terraces and breaks in slope-submerged benches that some researchers interpret as old coastlines cut by waves when the water stood still long enough at particular levels. Then there are the sediments themselves. On the bottom of the Black Sea, cores pull up layer cakes of mud, sand, and microscopic life. In the layers thought to represent the pre-connection lake, you can find microfossils, tiny shells, and organic structures from organisms that prefer low salinity, freshwater conditions. Above a certain horizon, those microfossils shift, more marine species that need saltier water appear, while freshwater types decline. Along with that biological change, the chemistry of the sediments records a story too. Ratios of certain elements and isotopes, like oxygen and strontium, act as fingerprints for the balance between river input and seawater. Somewhere in the sequence, that balance tilts, hinting at an influx of Mediterranean salt. Taken together, terraces, microfossils, and chemical signatures do suggest that the Black Sea shifted from a less salty, more isolated basin to a more marine-influenced one during the Holocene, the period after the last ice age. But shifted is not the same as catastrophically filled. Almost every step in this story is debated. Did the Black Sea really stand far below global sea level as a stranded freshwater lake? Or was it already close to equilibrium with the rising world ocean, experiencing a more modest change when connection was re-established? When did the Mediterranean overtop that Bosporus sill? Some early versions of the hypothesis placed the big flood-like event around 7,600 years ago. More recent work, using different dating methods and more cores, has suggested earlier or more gradual transitions, spread over centuries rather than a single human lifetime. Then there's the question of speed and magnitude. One camp argues for a relatively sudden transgression, a metre or more of sea level rise in the Black Sea per year for several years or decades, enough to overwhelm any attempt to simply move the farmstead a bit upslope. Another interpretation sees a slower, more complex process. Pulses of inflow and outflow, local subsidence and uplift, regional climate shifts affecting river discharge, all interacting to produce a less cinematic, but still consequential, reorganization of the basin. Part of the difficulty is resolution. Sediment cores can tell us that conditions changed between, say, 8,400 and 7,500 years ago. That's excellent by geological standards, but it blurs the difference between within a generation and over 300 years. For cultural memory and myth-making, that distinction matters. So where does this leave flood stories? It is tempting to draw a straight line from a rising Black Sea to Mesopotamian and Near Eastern narratives of gods sending waters to wipe out cities. The geography lines up in a broad sense. People living around the eastern Mediterranean and the Fertile Crescent, within trading distance of the Black Sea world, absolutely experienced a time when seas were higher and coasts were shifting. If parts of the Black Sea shoreline did flood rapidly, if farming villages or camps along low deltas were abandoned to encroaching water, those events could have fed into a larger regional sense that the boundary between land and sea was no longer stable. Traders, migrants and storytellers move faster than shorelines. A disaster remembered on one coast can easily become a warning tale far inland. But caution is warranted. The best supported elements of the Black Sea story so far are these. There was a transition from fresher to saltier conditions. There were changes in water level, and the basin did reconnect with the global ocean in the early to mid-Holocene. The precise timing, rate, and human impact of that reconnection are much fuzzier. We do not have clear archaeological layers of drowned Neolithic villages neatly sealed under a single flood deposit along the old Black Sea shore. We see hints, tools and structures along now submerged terraces, cultural shifts in inland sites that might reflect relocation, but nothing that screams one-time apocalypse. It may be that the Black Sea was part of a mosaic, a place where post-ice age sea level rise, regional tectonics and climate variability combined to produce episodes of abrupt local flooding and longer-term encroachment. Those episodes, layered on top of river floods from the Tigris, Euphrates, Nile, and others, would have created a landscape where water could upend human plans more than once in a lifetime. In that kind of world, you do not need a single global flood to seed myths of great inundation. You need generations of people who watch the waters change, who hear about distant coasts swallowed by the sea, who see villages moved and fields abandoned, and who try to make sense of it all in stories. The Black Sea hypothesis, at its most careful, gives us one plausible piece of that larger puzzle, a real basin in a real time, where water rose and lives were disrupted. How much that specific event shaped the flood narratives that would later be written down in cuneiform and scripture remains uncertain. But it reminds us of something important when we talk about a great flood. We may actually be talking about many floods, layered in memory. River floods, sea level jumps, storm surges and tsunamis, each leaving their own scars on land and culture. To see that more clearly, we need to look beyond inland seas and ask what happens when rivers themselves suddenly change their minds, when a channel that has followed one course for thousands of years overnight decides to carve another. Rivers look so permanent on a map, a blue line inked between two margins, maybe with a few graceful bends, a delta fanning into the sea. We learn their names in school as if they were mountains or continents, fixed features of the world. But rivers are not lines. They are negotiations between gravity, water, and mud. And sometimes the negotiation breaks. Geologists have a word for when a big river suddenly decides it would rather go somewhere else. Avulsion. Imagine a river winding across its floodplain. Each year it spills a little over its banks during high water, dropping silt across the land. That silt builds natural levees along the channel, slightly raised ridges that keep the river mostly contained in normal flow. Inside those levees, the riverbed is also filling with sediment. Over centuries, the river can end up flowing on a kind of elevated causeway of its own making, perched above the surrounding plain. That's a precarious situation. All it takes is one extreme flood, one bank failure, one breach of that natural levee, and suddenly gravity sees a new option, a lower path across the floodplain, maybe toward a different basin, a different delta, a different coastline. In a matter of hours or days, most of the flow can abandon the old channel and roar into the new one. The old course becomes a stranded loop or a sluggish backwater. The new channel slices through fields, settlements, sometimes entire regions that never thought of themselves as riverfront before. From the point of view of a mapmaker with a pencil, this is a small change, Just redraw the blue line. From the point of view of the people living there, the world has been rewritten. Now, set this process in one of the most flood-prone, river-built landscapes humans have ever tried to organize: Mesopotamia. The land between the Tigris and Euphrates is not a static stage for history. It is a low, gradually sloping plain made of river mud, built and rebuilt by exactly this kind of behavior. Over thousands of years, those two rivers have wandered, split, rejoined and shifted, leaving behind abandoned channels, oxbow lakes and buried levees. Early cities grew up here precisely because of the rivers. Irrigation canals fed by the Tigris and Euphrates turned dry land into grain fields. Barges carried stone, timber and goods along the waterways. The rivers were the arteries of the first urban experiments, but by harnessing them, people also amplified the risks. To irrigate, you need to control water. That means digging canals, cutting diversion ditches, reinforcing levees, and sometimes building new ones. Each intervention changes how and where floodwaters can spread. It raises some ground with embankments and fills other areas with silt from overflow and canal maintenance. Over generations, successful irrigation can literally raise the floor of a river. Sediment trapped in canals, piled into walls, and reworked onto fields means the active channel is riding higher and higher above the surrounding countryside. That's perfect until it isn't. A high, levied river contains moderate floods very well. It also stores up the potential for catastrophe. When an extreme event comes, unusually heavy mountain snowmelt, a stalled storm system, a series of upstream breaches, the water looks for weaknesses. A section of levee fails, perhaps near a city that has grown up snug against the riverbank, and the whole carefully managed system becomes a weapon turned inward. Archaeologists working in southern Mesopotamia encounter flood layers in ancient cities, sudden sheets of river silt draped over earlier streets and walls, sometimes half a metre thick, sometimes more. In some cases, rebuilding follows quickly. In others, entire neighbourhoods or towns seem to have been abandoned or shifted. This is not a single, clean world flood so much as a repeating pattern of infrastructural failure embedded in a restless landscape. And floods, in this setting, are never just about water. When your fields depend on a state-run web of canals and levees, a flood is also a political event. If the embankments upstream are neglected because of war, corruption or incompetence, and your district gets washed away, it is not hard to see the disaster as a failure of kings, officials or rival cities up the canal. Clay tablets from Mesopotamia include complaints about irrigation rights, canal maintenance, and the allocation of labour to keep ditches clear. One group's decision to divert more water might mean another group's fields dry out, or that overflow threatens their homes. Where the river runs is, very literally, a matter of power. When that system breaks in a spectacular way, when a levee fails and floodwater pours into a city that had trusted in its walls and its engineers, the aftermath is not just mud and rebuilding. It is blame, reflection and meaning-making. Did the gods withdraw their favour? Was the king negligent? Did the community break a covenant? Ignore a warning? Fail in ritual obligations? In a flat alluvial world, the basin is your universe. The horizon is close if the river that defines your economy, your trade routes, and your sacred geography suddenly invades every street, submerges the landmarks you thought were eternal, and cuts a new path through your countryside. It does not feel like a local adjustment. It feels total. That's an important distinction when we think about phrases like the whole earth or all the land in early texts. Geologically, a basin-wide flood might affect only a fraction of a percent of the planet's surface. Culturally, if it drowns every city you know by name, if it wipes out the fields that feed your world, it is, in every meaningful sense, universal. The Tigris and Euphrates did not need to cover every continent to inspire stories of creation undone and remade. They only needed to overwhelm the lived world of a few generations. Once those experiences are filtered through priests, poets, and scribes, the language naturally expands. Waters become cosmic, floods become verdicts. Political failures and unlucky avulsions are retold as divine decisions to wash away corruption and start again. This is not to say that specific myths can be cleanly matched to specific flood deposits. The archaeological and textual records rarely line up with that kind of precision. But the pattern is clear. In places where rivers are capricious and the stakes are high, disasters tend to be remembered not just as weather events, but as moral and cosmic turning points. Rivers like the Tigris, Euphrates, Nile, Indus, and Yellow River have all at times rewritten their floodplains in the space of a season or a night. Each time, people living along their banks have had to rebuild not only their canals and houses, but their explanations. Out of those explanations come stories of worlds destroyed by water and remade by favour, obedience, or fate. To see how this plays out on a grander climatic scale, we have to step back from individual rivers and look at the larger engines that feed them, especially the vast shifting breath of the monsoon. The word monsoon sounds like a storm. In everyday speech we use it to mean heavy rain, flooded streets, maybe a news clip of people wading through brown water with umbrellas. But in climate science, the monsoon is not a storm at all. It is a pattern, a seasonal breathing in and breathing out of heat and moisture between land and ocean. It is the difference between parched dust and chest-deep water, between empty basins and inland seas. And that breathing has not always been as steady as it feels in a human lifetime. At the end of the last ice age, as the big northern ice sheets shrank and the planet warmed into the early Holocene, the last 11,700 years or so, the monsoon belts across Africa and Asia shifted like slow grinding gears. Land heats and cools faster than ocean. In summer, hot land pulls moist air off the sea. In winter, cooler land loses that pull. Change the amount of sunlight reaching the tropics. A small tweak in Earth's orbit, a subtle wobble in our tilt, and you change that seasonal contrast. In the early Holocene, around 9,000 to 6,000 years ago, Northern Hemisphere summers were slightly warmer than today. It doesn't sound like much, a degree or two Celsius in the right months, in the right latitudes. But to the monsoon, that is fuel, rain belts marched farther north. The Indian and East Asian monsoons strengthened. What are now dry or semi-arid zones received regular, soaking rains. Lakes expanded. Wetlands sprawled across basins that today are mostly dust and scrub. On maps reconstructed from lake sediments and fossil pollen, you can see a green Sahara dotted with lakes and rivers, and an Asia with swollen inland seas and broad belts of forest where steppe now stretches. In South Asia, the summer torrents that feed the Indus and Ganges basins likely came heavier, more predictably, and sometimes more violently. This is where the flood stories start to multiply. Stronger monsoons do not just mean more rain, they mean more runoff. Hill slopes that could previously absorb a normal rainfall now saturate quickly. Rivers respond with sharper peaks. Small depressions on the landscape, which in a drier climate would stay puddles or seasonal ponds, become permanent lakes. Existing lakes rise, pushing shorelines up and out. Imagine living along the margin of such a lake. For generations perhaps, your community has built on what feels like safe high ground, a comfortable distance from the water's edge. Each year the rains fill the lake. Each dry season it recedes. The pattern is familiar, predictable enough to build around. Then, over the span of a few particularly wet decades, the equation changes. The monsoon intensifies. Rains linger longer into the season. Storm cells stall over the catchment. Upstream hills and plateaus that were once grassy start eroding, delivering more sediment to the rivers, making them muddier, more prone to spilling over. The lake rises not by inches but by meters. Storm surges push waves against new cliffs of soft soil. Old campsites, graves and shrines along the former shoreline are quietly drowned. People retreat upslope. Platforms are rebuilt a little higher. Paths now end at water where they once ended at fields. Then, one year, the system crosses a threshold. The swollen lake overtops a low saddle in the surrounding hills, an outlet that had either never existed before or had been dry for generations. Water begins to spill out, carving at first a small channel, then a roaring gorge. From the perspective of geomorphology, this is a lake overtopping and cutting a new outlet, perhaps down to a lower basin, perhaps to the sea. From the perspective of people living around that lake, it is a world-ending flood. The water does not just rise, it empties. Shorelines collapse. Mud and boulders are ripped from slopes and carried outward. Downstream valleys, which may have had only modest streams before, are suddenly hammered by a wall of water and debris. It is entirely plausible that multiple such events occurred around the early Holocene in monsoon-fed regions. Lakes in the Tibetan plateau overtopping, ephemeral basins on the Indo-Gangetic fringes linking, inland seas in northern China or Central Asia, pulsing higher and then breaking through low divides. Geologists do in fact find evidence of paleolakes in these regions, ancient shorelines etched high above present water levels, deltas stranded far inland, thick sequences of lake mud where no large lake exists today. Dating those features points again and again to early and middle Holocene intervals of stronger monsoon rainfall. In South Asia, some researchers think the Great Lakes of the Thar Desert swelled during these wet phases, their overflow contributing to flood pulses down rivers like the Gargahakra, a system that may be dimly remembered in later myths as the lost Saraswati. In China, the Yellow River Basin shows repeated episodes of catastrophic flooding, preserved as thick layers of silt and debris, sometimes capped by hurried reconstruction. One debated case, the so-called Jishi Gorge flood, appears to record a landslide-dammed lake on the upper Yellow River, suddenly breaking around 1920 BCE. Whether or not that specific event connects to later legends, it fits the pattern: climate-fed lakes, unstable dams, sudden release, and a downstream catastrophe. But the monsoon does not only have a wet switch, it has a drying one too. The same orbital mechanics that strengthened the early Holocene monsoon gradually weakened it again. Over thousands of years after about 6,000 years ago, the rain belts retreated southward. Regions that had been lush wetlands or broad river plains began to dry. Lakes shrank, sometimes in fits and starts rather than a smooth trend. A generation might know the lake as vast and bountiful. Their grandchildren might walk across cracked mud where their grandparents fished. Rivers became more seasonal, their mighty summer floods alternating with long, low-flow periods. Drying does not mean floods disappear. In some ways it can make them worse. As soils desiccate and vegetation thins, the land loses its sponge. When the monsoon does arrive, even if weaker on average, storms can dump water onto hard ground that refuses to absorb it. The result is faster runoff, flashier floods, more erosion. The channel that was modest for most of the year becomes a brute for a few critical days. In South Asia, the weakening of the monsoon coincides with changes in settlement patterns along rivers like the Indus. Some once dense urban cores shrink or shift as water becomes less reliable. Irrigation systems have to reach farther and work harder to capture the remaining flow. Competition for prime floodplain land intensifies. Floods in this context are no longer just seasonal expectations, they are gambles. You might gamble on building lower to keep access to water, hoping the river will not rise too high in any given year. Or you retreat, accepting worse access but better safety. Both choices carry risk. Both can fail. In East Asia, as monsoon variability increased, Some periods saw clusters of large floods recorded in historical chronicles. The Yellow River in particular gained a reputation as China's sorrow, not because it flooded every year, but because when it did so in conjunction with changing climate and human land use, deforestation, farming steep slopes, building levees, it could shift course, break embankments, and spread destruction across provinces. Climate, in all of this, is not a script handing out fixed roles. It is a stage manager setting lighting and props. A stronger monsoon loads the landscape with water, raises lakes and primes rivers for high floods. A weakening monsoon stresses communities, pushes them closer to the river margins, and erodes their buffers. Human choices where to build, what to plant, how to manage forests and levees decide how those background conditions play out. But to people living through a few bad decades at the hinge between wetter and drier regimes, the distinction between climate background and event is invisible. They experience a cluster of extreme seasons as a collapse of order, lakes swallowing fields, rivers leaping their banks, then years of drought forcing migrations into already crowded basins. Stories born in such times do not usually say the monsoon belt shifted slightly northward over several centuries. They say, for many years the rains came wrong, or the river rose and did not stop until the world was drowned, or the gods withdrew the waters and the land cracked. By reading lake cores, river terraces and abandoned shorelines, we can see the outlines of those shifting monsoon worlds. We see repeated opportunities for communities to be hit by flood catastrophes tied not to a single freak storm, but to the slow pulse of climate itself. And along the coasts where these monsoon-fed rivers meet the sea, another set of hazards begins to appear. Tsunamis, storm surges, and sea floods that can arrive without rain at all. Floods rising from rivers and lakes give you warnings. Clouds stack on the horizon. The air goes heavy. Upstream rain hammers hillsides for days. The river begins to brown and swell. Elders glance at the water level and mutter. You may not know exactly how bad it will be, but you can feel that something is coming. Tsunamis are not like that. On a quiet morning under a blue sky, with no storm in sight, the ocean itself can suddenly behave like a living thing gone mad. In the geologic record, that difference leaves a signature. River floods sort the world patiently. As the water rises out of the channel and spills across the floodplain, it slows down. Coarser sand and gravel are dropped close to the river. Finer silts and clays drift farther, settling as thin, even layers across fields and marshes. Buried soils, plant roots, and even the traces of insect burrows can be preserved between one flood layer and the next. Over centuries and millennia, those floods stack up like pages in a book with regular chapter breaks, mud, then soil, then mud again. A rhythm of high water and low water that a geologist can read with a hand lens and a notebook. Tsunamis write in a different hand. They arrive fast and deep. A single wave, or more often a series of waves, can race kilometres inland, especially over low, flat coasts and river mouths. Instead of calmly overtopping their banks, they tear at everything in their path. When geologists dig into a coastal plain that has seen such an event, they sometimes find a strange layer, a sheet of sand and coarse silt draped over marsh mud or farmland soil, sitting far above the normal reach of tides and storms. Embedded in that sheet may be things that do not belong together, shells from the beach mixed with pebbles from inland, ripped up clumps of peat, broken pottery, bits of charcoal, splinters of wood. The grains themselves tell a story. Under a microscope, tsunami sands often show mixed sources and little sorting, fine and coarse jumbled together, sometimes in multiple sublayers that mark each incoming and receding pulse of water. You might see rip-up clasts, chunks of the underlying mud torn out and carried along, then frozen in place when the water finally retreats. Above this chaos, if the coast is resettled and the land returns to more ordinary business, quieter sediments accumulate again. Marsh plants rebuilt, soils reform, perhaps a new village layer grows. To someone coring through it thousands of years later, the tsunami reads as a sudden out-of-place violence sandwiched between stretches of everyday life. What creates that violence is usually not the weather at all, but the solid earth shifting. When an underwater earthquake strikes along a subduction zone, a place where one tectonic plate is diving beneath another, the seafloor can lurch upward or downward by several meters in a matter of seconds. The ocean above it has no time to adjust gently. Gravity pulls and the disturbed water mass begins to oscillate. Far from shore, that oscillation is just a broad, low swell speeding across the deep ocean at the pace of a jetliner. A ship might barely notice, but as that wave approaches shallow coastal shelves, it slows. The back of the wave catches up to the front. Energy piles upward. What was once a subtle rise becomes, in some places, a wall. Submarine landslides can do something similar on a more local scale. Thick piles of sediment sitting on steep continental slopes can become unstable, triggered by an earthquake, by rapid sediment loading during a flood, even by the slow weakening of gas hydrates. When they fail, millions of tons of mud and sand suddenly slump downward, displacing seawater like a dropped stone in a bathtub, only on a scale that beggars imagination. In both cases, the coast pays the price. From the viewpoint of people on shore, the details of tectonics do not matter. They see the sea draw back unnaturally fast from the beach, exposing rocks and reefs that have never been visible before. Curious onlookers may walk out onto the newly uncovered ground. Minutes later, a wall of water arrives, choked with debris sweeping inland with the unstoppable force of a moving hillside. This is the kind of event that does not just injure a village. It can erase one. Entire communities, fields, boats, shrines, all gone in a few hours, dragged back toward the sea or left tangled in new channels and lagoons. Survivors, if there are many, may find their landmarks and burial grounds washed away, replaced by raw sand and saltwater pools. It is not hard to see why tsunamis become cultural anchors. Unlike a seasonal flood that your grandparents might recall as the bad year when the river rose to the big rock, a great tsunami can represent a true break in memory. There is a world before that wave and a different, diminished world after. New coastlines, new inlets, sometimes even whole islands fractured or sunk by the earthquake that started it all. Stories born from such trauma often carry details that stand out. The sea withdrawing before the flood, fish flopping on exposed ground, waves that come in not once but many times. The ocean itself described as angry or inverted. They may also emphasize helplessness. No clouds, no warning, just a normal day turned inside out. Geologists do not have to rely on stories alone to find these events. In northern Europe, for example, there is evidence of a massive submarine landslide off the coast of Norway about 8,000 years ago, the Storegga Slide. When those sediments collapsed, they seem to have generated tsunamis that raced into the North Sea and Norwegian Sea, overtopping low-lying coasts from Scotland to western Norway. On some Scottish estuaries and in parts of eastern Scotland's lowlands, cores and trenches reveal sand sheets lying inland, over peat and soil, well above typical storm surge reach. Radiocarbon dates from plant fragments above and below those sands cluster around the time of the Storegga event. In a world where people were already living along those coasts, hunting, fishing and foraging near brackish waters, it would have been a day when the sea briefly tried to reclaim the land. Farther east in the Mediterranean, sediment cores and excavations have turned up tsunami layers associated with large earthquakes on the Hellenic and other arcs. Coarse marine sands penetrating far into coastal lagoons, pottery and architecture abruptly buried. Harbour installations wrecked and rebuilt on top of chaos. Radiocarbon dating of organic matter and, in more recent millennia, connections to written accounts help anchor these events in time. Across the Pacific, paleotsunami studies along the coasts of Japan, North America, and Oceania show similar patterns. Anomalous inland sand sheets, tangled drift logs, sudden erosional cuts, all bracketed by datable materials, charcoal from fires, seeds, shells. For the Pacific Northwest of North America, a buried tsunami layer around 1700 CE aligns with Japanese records of an orphan tsunami that struck without a local quake. The culprit was a great earthquake on the Cascadia subduction zone across the ocean. Prehistoric tsunamis, further back than any written record, are dated the same way as other geologic events, by radiocarbon on plant remains, by luminescence dating of sand grains that were last exposed to sunlight when the wave laid them down, sometimes by tracing them to known episodes of seafloor failure mapped with marine geophysics. Piece by piece, a catalogue emerges. Not a single global deluge, but a patchwork of devastating coastal floods tied to particular margins, particular faults, particular underwater slopes. Could some flood traditions have their roots in these local or regional catastrophes? It is entirely plausible. A community that loses much of its population and landscape to the sea might tell, for generations of the day when the waters rose and swept away all people, or when the boundary between sea and land was broken. As those stories travel inland, details of salt water and receding tides could blur, leaving a distilled image of overwhelming flood. But tsunamis, powerful as they are, have limits. They do not raise sea level over the whole planet. They do not cover mountains across continents. Their reach is focused, along certain coasts, into certain river mouths, sometimes tens of kilometers inland, but never to the ends of the earth. In that sense, tsunami memories can explain some threads woven into later flood narratives, especially those that describe the sea behaving strangely under clear skies. They cannot by themselves account for a universal, mountain-topping flood that drowns every peak from Anatolia to the Andes. To understand how such global-scale stories formed, we have to widen the lens again beyond single waves, beyond even single rivers or lakes, and look at the long arc of coastlines themselves. Not just one day when the sea came too far, but thousands of years when, slowly and relentlessly, the sea simply kept coming. To imagine a truly global flood, the kind that pours over every continent and drowns every mountain, you have to start by asking a simple, stubborn question. Where would all that water come from? The Earth already has a fixed water budget. Some of it sits in the oceans, some is locked in ice, some circulates through the air as vapour, some trickles through soils and rocks, but the total amount is not casually changing on human or even civilization timescales. To raise sea level high enough to cover the tallest mountains, you would need an amount of extra water that simply does not exist in any known reservoir. Even the ice sheets, as vast as they are, fall short by an enormous margin. If you melted every glacier, every Antarctic ice sheet, every frozen scrap in Greenland and on mountain ranges worldwide, global sea level would rise on the order of 70 to 80 meters. That is enough to redraw every coastline, drown coastal plains, and erase low islands. It is nowhere near enough to submerge mountain chains that climb thousands of meters above present sea level. To push water that high, you have to do something much more radical than melt ice. You have to remake the shape of the planet. The reason oceans sit where they do is not arbitrary. Earth's surface is divided into thick, buoyant continental crust and thinner, denser oceanic crust. The ocean basins are quite literally broad, deep bowls of heavy rock that ride lower in the mantle. Continents, by contrast, float higher and form the elevated platforms where we live. As long as that contrast exists, water will concentrate in the low bowls. To flood the continents to mountaintop level, you would either need to suddenly shrink the basins, forcing water to spill upward, or somehow raise the water level thousands of meters without changing the basins at all. Plate tectonics does not work that way. Plates move, collide, and pull apart over millions of years. Ocean ridges slowly push out new crust. Subduction zones slowly recycle old crust back into the mantle. Basins can deepen or shallow over geological ages, but the process is slow and patchy, not a synchronized planetary piston. Even the most dramatic tectonic events we know, continent-continent collisions that raise Himalaya-sized ranges, or rifting that opens new ocean basins, unfold over tens of millions of years, not months. There is no known mechanism in mainstream geophysics that would make every ocean basin on Earth suddenly become shallow at once, forcing water up and over every mountain. What about water arriving from space? Comets and icy asteroids certainly carry water, and over the earliest history of the solar system, they probably contributed to Earth's oceans. But the bombardment rates necessary to significantly change global sea level now would be catastrophic in an entirely different way. You are not talking about gentle rain. You are talking about a hailstorm of impactors so large and frequent that the main problem would not be water, but global firestorms and crust-melting heat. And again, geology keeps receipts. If, at some point in the last few 100,000 or even few million years, there had been a truly global synchronous flood that rose over every highland, it would have left a specific kind of fingerprint. Think about what you would expect to see. Across every continent, at roughly the same age, there should be a continuous sheet of sediment laid down by that water. It would mantle hills and valleys alike, draped over older landscapes like a single blanket. The materials in that blanket would show signs of long-distance transport, mixed fossils from different environments, widespread sorting patterns, marine microfossils high in mountain basins with no other explanation. Instead, when geologists read the rocks, they see something much more complicated and much more local. Flood deposits exist, but they are patchy and tied to particular basins and times. The sediment left by the Missoula megafloods fills scabland channels in the Pacific Northwest and giant gravel bars along the Columbia. But it does not appear in the Alps at the same age. The Black Sea's rapid transgression left drowned shorelines and submerged river deltas in that region, but not in Patagonia. Marine fossils do climb into mountains, but in layers that were clearly deposited in ancient seas long before the mountains were uplifted. You can trace those layers sideways into adjacent lowlands, measure the gentle tilts and folds that raised them, and date the whole sequence with independent methods: radiometric clocks in volcanic ash layers, magnetic reversals locked into the rocks, the slow evolution of fossils through the stack. It is a record of long, patient change, not a single sudden deluge. What we also do not see is a single, globally synchronous erosional surface, a matching scoured horizon on every continent that says, here is where the water stood when it covered the world. Instead, rivers cut their own terraces according to local climates and uplift rates. Coastal plains record their own cycles of transgression and regression as ice sheets wax and wane. Some regions show violent local events, others at the exact same moment in time show nothing unusual at all. For people who grew up with traditions of a universal flood, this can be a difficult contrast. On one side, there is a powerful narrative of moral and cosmic meaning, told and retold for thousands of years. On the other, there is a quiet, methodical reading of rocks and sediments and isotopes that points toward many floods, many disasters, but not one single day or even one single year when the entire planet went under at once. When geologists say they do not find evidence for a global, mountain-covering flood in the recent past, they are not making a claim about the value of those stories. They are reporting what the rocks, as far as we can tell, actually show. There is room here for respectful separation of questions. One question is geological. Did the physical Earth experience a simultaneous world-spanning mountain-drowning flood within the span of human cultural memory? On that, the mainstream consensus, built from a century and more of fieldwork on every continent, is that the evidence points strongly to no. The other question is cultural and theological. Why are flood stories so central, so widespread, so emotionally charged? That question is not answered by measuring sand grains. It lives instead in anthropology, literature, philosophy, belief. What geology can offer, though, is a different kind of awe. Not a single, all-erasing deluge, but a planet that has seen countless floods of every scale, valleys emptied and refilled, inland seas grown and vanished, coastlines advanced and retreating like slow-breathing tides over entire epochs. A history where local catastrophes loom as large, to the people who lived them, as any global event ever could. In that sense, the Great Flood is not one moment in time, but a mosaic made from many waters. Missoula in North America, Storegga in the North Atlantic. Monsoon surges across Asia. River avulsions on the Nile and the Tigris-Euphrates. Sudden lake outbursts in the high Himalayas, each one leaving its own deposits, its own scars, its own stories. To understand the real story of the Great Flood, we have to weave those pieces together, not into a single wall of water that circled the earth, but into a timeline, a long, irregular, very human timeline of how rising waters have shaped landscapes, cultures, and memories again and again. That is where we turn next. From the question of whether there was one flood to the task of mapping when and where all these different floods actually happened. If there was no single year when the whole world drowned, then the time of the Great Flood is not a date you can circle on a calendar. It is a window, or rather a set of overlapping windows, spread across thousands of years, in which water was misbehaving in ways that would have felt apocalyptic to anyone standing too close. Geologists and climate scientists tend to focus on one broad slice of time when they talk about floods that humans could have seen firsthand, the period from the coldest part of the last ice age through the Big Melt and into the middle of the Holocene, roughly from about 20,000 years ago, when ice sheets were at their maximum, down through 6,000 or 4,000 years ago, when sea levels and climates were settling towards something like what we know today. During that span, sea level rose by more than 100 meters. Ice-dammed lakes formed and burst. River systems were rerouted. Monsoon belts shifted north and south. Coastlines retreated inland at speeds you could sometimes watch across a lifetime. But this big window is not one story. It is several. In Northern Europe, for example, one set of memories might be anchored to the drowning of Doggerland and the Storegga tsunami, somewhere between 8,500 and 8,000 years ago. Imagine communities living on the low plains that now lie beneath the North Sea, wetlands and estuaries rich in game and fish, watching the sea creep closer over generations, and then, one terrible day, a wall of water rushing in after a distant submarine landslide. Farther southeast, among the farming villages around the Black Sea, another anchor point might be the period when that basin filled and shorelines raced inland, perhaps around 8,000 to 7,500 years ago. Whether it was a sudden spill or a somewhat slower flood, the effect on the local inhabitants would have been the same in emotional terms. Fields lost, villages abandoned, former hilltops turned into islands. In Mesopotamia, the great rivers Tigris and Euphrates tell yet another version. As the ice sheets melted and climates shifted, those rivers changed their courses again and again, sometimes abruptly. Archaeological layers from early cities and proto-cities show repeated episodes of thick flood silts, walls buried in water-laid mud, habitations abandoned after inundation. Not once, but many times between about 7,000 and 3,000 years ago. In South Asia and East Asia, the pulse comes from the monsoon. Lake sediments and cave stalagmites, those slow-growing mineral towers that record tiny changes in drip water chemistry, show that monsoon intensity has waxed and waned over the Holocene. There are intervals when rainfall surges, rivers swell, and floodplains are repeatedly inundated. Archaeological sites along the Indus, the Yellow River, the Yangtze, show destruction layers and rebuilding phases that track those wet surges. For farmers depending on seasonal rains that suddenly arrived as deluges, this was its own kind of flood story. So how do we stitch all of this together into a timeline without just guessing? This is where different lines of evidence have to agree. Start with climate proxies, ice cores from Greenland and Antarctica, which trap bubbles of ancient air and layers of snowfall that build up year by year. They tell us when the planet was warming fast, when meltwater pulses were pouring into the oceans, when monsoons were strengthening or weakening. Then look at marine sediments, where layers of tiny shells, dust, and organic matter settle on the sea floor. Changes in grain size and composition can mark flood pulses from rivers, landslide events, or sudden shifts in ocean circulation. Radiocarbon dating of shells and organic fragments pins those changes to approximate calendar years. On land, rivers and lakes keep their own diaries. Terraces cut into valley sides, floodplain deposits, ancient shorelines etched along hills. Optically stimulated luminescence can tell us when grains of sand last saw sunlight. Radiocarbon can date bits of charcoal and plant matter buried in the mud. Finally, layer the archaeology on top. Clay tablets, temple archives, and oral traditions talk about years of great water, kings who rebuilt after floods, gods appeased with rituals to keep the rivers in their banks. Excavated houses show sudden abandonment, rebuilt on higher ground. Pottery styles and traded goods reveal when communities moved or when networks were disrupted, hinting at underlying environmental shocks. When these different records line up, when a cave stalagmite says the monsoon strengthened, a river valley shows thick new flood sediment, and nearby settlements all seem to have been rebuilt around the same time, you begin to see patterns. Not a single spike labelled the flood, but clusters. A cluster around the rapid sea level rises of the early Holocene, when coastal peoples across the world were watching shorelines retreat inland by hundreds of meters or more in a human lifetime. Another cluster around 8,500 to 7,500 years ago, with events like Storegga Doggerland's last days and possible rapid changes around the Black Sea. Smaller, regional clusters tied to shifting monsoons in Asia, to Nile and Mesopotamian river behaviour, to local lake outburst floods in mountain regions. If you wanted a cautious best-fit model for the great flood traditions, it might look like this. For thousands of years in the late glacial and early to mid-Holocene, human communities lived through repeated, sometimes devastating water events. Coastlines sank under rising seas, rivers overran their banks and shifted paths. Occasional tsunamis and outburst floods struck with almost no warning. Each event scarred landscapes and memories. Stories were told and retold about ancestors saved on high ground, about gods who once drowned the wicked, about an age before the waters came. Over time, those many local catastrophes, spread across different regions and generations, began to echo each other. When people from different valleys met through trade and marriage, they did not exchange finely calibrated hydrological charts. They exchanged stories. In those stories, different floods could merge. Details from Mesopotamian river plains, from Black Sea shores, from drowned coasts of the Mediterranean or the North Sea could blend into a single archetype. There was once a time when the world was washed clean. This model is tempting because it ties into what we know about human memory and mythology. We compress, we generalize, we turn a long series of similar events into a single narrative with names and motives and moral weight. But it is still a model. The further back we try to push specific stories, the thinner the ice becomes. Oral traditions can be resilient, but we do not yet know how far into deep prehistory a recognizable narrative can travel. Submerged landscapes, continental shelves, drowned river valleys, paleocoastlines are only beginning to be mapped in detail. There may be flood events out there preserved under the waves that we have not yet imagined. Future cores drilled from buried deltas, sonar scans of forgotten plains, or ancient DNA pulled from seafloor sediments could shift the dates, add new flood pulses, or even reveal regional catastrophes that rival anything we currently know. So, when we build a timeline from many waters, we should hold it lightly. We can say that the age when humans most likely experienced world-ending floods in many places spans roughly from the last glacial maximum into the mid-Holocene. We can suggest that different regions contributed different pieces to the global tapestry of flood myths. We can show how geology, climate science and archaeology point again and again to a period when the planet's water systems were especially unstable for human societies. But we should also leave room at the edges, room for stories older than our current evidence, and for evidence not yet pulled from the mud. Because the waters have been busy for a very long time, and after they rise, and roar, and finally retreat, something else always follows in their wake. That is where we turn in the final part of our journey, not to the moment of flooding itself, but to what remains after the waters go down. What remains after the waters is never just mud and broken walls. It's patterns. From a geologist's point of view, that's the biggest lesson of this whole story. When you zoom out far enough, the rocks and sediments do not tell you about one primordial catastrophe that reset everything in a single year. They tell you about many catastrophes in many valleys and along many coasts, unfolding at different times. Ice-dammed lakes draining in violent pulses, sea levels rising stepwise as ice sheets collapsed, rivers abandoning old channels and cutting new ones, tsunamis racing across shallow seas, monsoons overshooting their usual bounds and turning plains into temporary inland oceans. Each of those events leaves its own kind of fingerprint: scoured bedrock here, chaotic boulder deposits there, thin layers of marine sand where there should only be river mud, drowned forests still rooted beneath the waves, terraces cut into hillsides and then abandoned. Taken together, those fingerprints do not point to a single global synchronous flood. They point to a restless planet that has, again and again, produced floods enormous enough to feel like the end of the world to the people standing in their path. And geology, slow and skeptical by nature, lets us put rough dates and places to many of them. Missoula and the channeled Scablands, late Ice Age Pacific Northwest. Doggerland's drowning and the Storegga tsunami, early Holocene North Atlantic. Rapid shoreline changes in the Mediterranean and Black Sea. Mid-Holocene, Circum-European. Monsoon-driven surges along the Indus, Yellow and Yangtze, Holocene Asia, in several distinct wet pulses. Local outburst floods from glaciers and landslide-dammed lakes in mountain ranges across the world, scattered through the same broad window. The picture that emerges is less cinematic than a single global deluge, but in some ways more awe-inspiring. It is a record of a planet in transition, thawing out from a great ice age with water systems lurching toward new equilibria. It is a record of repeated regional ends of the world separated in space and time, yet similar enough in human experience that later storytellers could braid them together. Following that evidence requires a particular posture of mind. Curiosity, first of all, a willingness to ask what a strange cliff, or a buried valley, or a drowned forest is trying to say. To treat landscapes as archives, not just scenery. Then patience with uncertainty. Radiocarbon dates come with error bars. Sediment layers can be eroded or disturbed. Sea level curves shift as new cores are drilled. The Black Sea flooding hypothesis, for example, has been revised repeatedly as more data accumulate. The details matter and they change. And finally, humility. Because for all the graphs and cross-sections and neat timelines we can draw, we are reconstructing an incredibly complicated history from broken fragments. We see enough to say that floods large enough to destroy entire cultures have happened, again and again. We see enough to say that most traditions of a great flood are probably mosaics built from many such events, filtered through memory and myth. But we do not see everything. We almost certainly never will. On the human scale, though, the reason these stories persist is not mainly about dates or discharge volumes. It's about what water does to meaning. Floods are different from many other disasters. Fire can destroy, but it leaves clear edges. This side burned, that side did not. Earthquakes shatter structures, but the land usually stays where it was. Water erases and rearranges at the same time. Fields dissolve into featureless silt. Graveyards wash away. Familiar paths vanish under a single reflective surface. When the water goes down, the map is different. A river has shifted. An island is gone. Your village is now on the wrong side of everything. For people whose lives depended on the precise behaviour of rivers and rains, this was existential in a way that begged for explanation. Why did the waters rise? Who allowed it? What did it mean? How do we make sense of a world that can, without warning, unmake itself and start over? Flood myths answer those questions in a way rocks never can. They give the waters intentions. They make survival contingent not just on luck but on virtue or obedience or being clever enough to listen to a warning and climb in a boat. They also carry something quieter, the memory that recovery is possible. Even in the most severe traditions, the waters eventually recede. A mountain emerges, a dove finds land, a hero's children start planting again. The story does not end at high tide, it ends with rebuilding. And that, more than anything, may be why flood stories are so widespread. They are not just about punishment or terror. They are about the fragile, stubborn continuity of human life in a world that sometimes tries very hard to wash us away. If you've listened this far, through ice sheets and drowned plains and ancient deltas, you've been part of that continuity for a little while. You've followed a chain of questions that stretches from clay tablets and campfire tales all the way down into seafloor mud and glacial scars. If you'd like to help this kind of slow, curiosity-driven storytelling float a little higher in the flood of online noise, it really does help to tap the like button, leave a comment, and subscribe. Those simple actions tell the algorithms that quiet, detailed explorations of deep time are worth showing to other people. And since this is History for Sleep, I'd love to know where in the world you are listening from and what time it is there right now. Are you drifting off at midnight in a city high above an old river valley? Napping through the afternoon in a place that was once seafloor? Somewhere far inland, somewhere right by the tide? If you feel like sharing, write it in the comments. In a small way, you'll be adding your own line to the long, ongoing story of humans living with water, after the rivers rise, after the seas advance, and after, as always, the waters finally go down.